Hello, everybody, and welcome to another lecture of 6837. Today, we're going to start the next big chunk of our course and move our attention from algorithms that are really slow for rendering to efficient algorithms that can render images really quickly. Essentially, we're going to start considering the demands of real-time computer graphics, where we need to produce images at a frame rate faster than your eye can sense that something is changing. Rather than algorithms like ray tracing, which are really designed to make accurate and high quality images at the cost of extra time. So today, we're going to start our discussion by talking a little bit at the high level of what the demands are for high-speed rendering, and then we're going to start suggesting techniques for rasterization, which will be our basic algorithm for how images get rendered on your graphics card. So typically when we talk about interactive style rendering, we're using graphics hardware. Usually we interface with it using software like OpenGL or DirectX. Here, OpenGL is this kind of open source multi-platform graphics tool, and DirectX is Microsoft only. Now, of course, this landscape changes all the time, and the specs for these two tools change all the time. Indeed, these days, things like Unity, which are one level above OpenGL, maybe are more popular than interfacing with your graphics card directly, but still these options remain. So these images show the difference, at least, maybe 20 years ago in quality between what you might get with a typical simple ray tracer and what you might be able to render with a simple rasterization piece of code on your graphics card. So on the left-hand side, our images produced using really simple OpenGL code, and on the right-hand side, our images produced using a ray tracer. Now, if you'll recall, in the last several lectures, we added all kinds of super cool effects to our ray tracing code, right? We have things like reflection, we have shadows, we can incorporate fancy textures, we could easily do anti-aliasing and so on. Now, simple OpenGL code basically makes for solid shaded shapes without very much else interesting going on. So essentially, the difference is going to be that ray tracing is fairly easy, if slow, to capture global effects, effects where rays of light are bouncing every which way in the scene. We're going to sacrifice those for efficiency in our initial version of the rasterization algorithm, but just like when we talked about ray tracing, then we're going to spend several lectures adding back these features to get higher quality images. So let's talk about this in some more detail. Now, if you recall, I've summarized the ray casting, or sort of the simplest incarnation of ray tracing on the left-hand side here. So remember that in ray casting, at least conceptually speaking, we sort of have an outer for loop over all the pixels in the image. And for each pixel, we generate a ray from the eye into the world. Now, for each of those rays, we iterate over all the triangles to figure out which triangle a ray hits into first. And then the key step is to keep the triangle which is closest to the camera. Remember that we called this technique backward ray tracing. The idea that, in reality, rays of light go from a light source to your eye, but in the ray tracing algorithm, we trace rays backward from our eye back to the light source. And there's good reasons for this. When we talked about global illumination, we saw that most rays of light do not reach your eye, and therefore may not be particularly useful to simulate, except if you want to get these really highly detailed effects. So now let's talk about GPU-based rasterization for triangles. By the way, GPU here stands for Graphics Processing Unit. I think we've mentioned that before. So in the GPU algorithm, it's kind of like painting rather than simulating light. So, that's hot. So the basic technique here is that rather than drawing our scene one pixel at a time, instead we're going to draw it one triangle at a time. So the idea here would be like you have a big list of all the different triangles in your scene, and you're going to grab them one at a time and paint them on top of your current image of what the scene should look like. So you should think of it just like painting. Of course, when you do that, you don't want to just draw the triangle on top of all of the past ones. It could be that your triangle is occluded by something you've already drawn. So we're going to have to find some technique for only drawing the things that are on top. So some analogy of that keep closest hit algorithm. So in some sense, we can think of this as a forward mapping approach, right? We're now just grabbing every triangle one at a time and then figuring out which pixels are inside of that triangle on the computer screen, as opposed to iterating over all the pixels and figuring out which triangle the ray through that pixel intersects. This is not quite the same as forward ray tracing. Obviously, forward ray tracing is much more complicated, but in some sense, it is a forward mapping approach. Now, this is an extremely granular way to understand the difference between ray casting and rasterization. That ray casting iterates over pixels and rasterization iterates over triangles. But it is kind of nice to remember this distinction that at the really simplest sort of scheme, GPU-based rendering is just a different order of for loops than ray casting. Now, it's obviously quite facetious to say that. And the reason why is that we don't just implement the algorithm that we saw on the screen, right? For instance, on your ray tracing assignment in this course, it was certainly more than like 4 or 8 lines of code, right? And the reason is that we spent a lot of time thinking about how to make our ray tracer more efficient and extensible. So for instance, if you remember a few lectures ago, we talked about how we don't actually have to iterate over every single triangle in the scene, but we can use space partitioning data structures to help us reduce the number of ray triangle intersections. Now, implicitly, that data structure really depended on the fact that our for loop over triangles was on the inside. And it's not so clear how we could use that particular technique to make our rendering algorithm more efficient if we put the outer loop as the one that's over all the triangles. So instead, essentially, what we're going to need are new algorithms that make this inner loop more efficient, just the same as we did before. And what we'll see is that there's somehow many more options here in terms of parallel computing and efficient things that make this the preferable option for rasterization and high-speed rendering. So let's talk about this rasterization term a little bit more. I guess I really haven't defined it formally, but roughly, rasterization is the process of taking a triangle and figuring out which pixels it actually covers. So the idea of rasterization is that I get the coordinates of the 3 vertices of a given triangle that we're going to render. It can also be like a square or some other shape, but typically your graphics card really focuses on just rasterizing triangles. And at least in principle, the idea here is to figure out a list of pixels that your triangle intersects, because those are the ones that you're going to have to shade when you want to worry about rendering the triangle. Oops, I guess it doesn't really include that last guy. I don't know, something like that. So the idea of rasterization is that if I have a tiny triangle on my computer screen, then really I should only figure out the pixels that intersect that triangle and do extra computation in that little part of my image, rather than having to touch that triangle for every single pixel on the screen. And just like I alluded to in the previous slide, essentially we're going to find different ways to accelerate rasterization that are just somehow fundamentally different than ray tracing. So that little change in for loops that seems kind of subtle and ineffectual in our previous slide is going to be really critical in terms of the ways that we can make our rendering using this algorithm faster. Okay, so let's dig in a little bit more into this rasterization process. So the basic step in rasterization is also sometimes called scan conversion. This is a bit of a dated term. It refers to scan lines, which are your old monitor used to update rows of pixels at a time. But the basic task here is, given a triangle's vertices, for now just as positions in 2 dimensions on your computer screen, you need to figure out which pixels to turn on. By the way, sometimes this phrase, like the list of which pixels to turn on, these things are sometimes called fragments. And there's one really critical message that I'm going to keep repeating in this course, which is that you can generate multiple fragments in the same pixel. Let's repeat that. You can generate multiple fragments in the same pixel. Moreover, some pixels may have no fragments on them at all. So for example, here When we do rasterization, these pixels that I pointed the arrow to actually don't get touched at all during our algorithm. Notice that that's already different than ray tracing, where you'd have to generate a ray for each of these empty pixels. But here, they get no fragments. In the interior of one triangle at a time, you get one fragment. And in areas of overlap, you get multiple fragments. This last thing we're going to talk about quite a bit later on is also a phenomenon known as overdraw, where the idea is that I might render a triangle that's sitting behind another one, but because I'm iterating one triangle at a time, I do all the computation for that triangle, and then it just gets covered up later. And that's the sort of thing that can happen in rasterization that didn't really happen in ray tracing. So in order to help fix that, we're going to introduce a data structure called the Z buffer, which is pretty much exactly what it sounds like. So in addition to keeping the color of every pixel on your screen, you're going to keep track of the depth of the current triangle that intersects that pixel. And essentially, if that depth is closer to the camera than the new triangle that you're rendering, you're just going to ignore the new triangle at that particular pixel. So maybe you don't generate a fragment at all, or if you already generated a fragment, you'll throw it away. Okay, so that's the really basic 50 miles away summary, is that you use rasterization or scan conversion really to figure out which pixels intersect a triangle on your screen. And then just for those pixels, you compute the illumination. So you don't like do it in other parts of the screen. And so what that means is that different pixels receive different amounts of computation, a little bit different than ray tracing. And then at the end of the day, you throw away things that are occluded using the Z buffer. We're going to add a lot more detail to all of these steps in our lecture today and moving forward in this course. So let's compare ray casting and ray tracing to the GPU-based rasterization methods. One of the really critical considerations that we might use to compare these different options is to ask what needs to be stored in memory in each of these two algorithms. So let's think for a minute. In the ray casting algorithm, as I send rays out, I don't know where they're going to end up, right? They could bounce all over my scene as I'm doing my rendering. And so what that means, in effect, is that I have to keep my entire scene in memory when I'm doing my rendering, because I never know which triangle I'm going to have to intersect with next. In GPU-based rendering, specifically in rasterization, that's not the case, right? I loop over every triangle, and then I never touch it again. So if we step back 10 feet, think about it for a minute, what we'll see is that ray tracing needs to store the entire scene description in memory at once, whereas the rasterizer only needs one triangle at a time, but it does need to store the image and depth information for all the pixels. Remember that the image here is like the color, and the depth is this Z buffer object. And so the question is, who wins? You know, like which of these algorithms use less or more memory? And if we do some back of the envelope calculations, we'll see that in a landslide, the rasterization algorithm uses less memory. Moreover, the amount of memory that it needs is sort of a fixed multiple of the size of the image that you're rendering. Whereas in ray tracing, as you increase the complexity of your scene, you also increase the amount of memory that you need. Right, so for example, a 1920 by 1080 frame, which is 1080p, I guess these days monitors can be even more detailed than that, takes about 24 megabytes. And of course it gets larger. So like one typical technique might be to render your algorithm, your image 2 times as big, and then average down to get some kind of anti-aliasing. But it's still on the order of megabytes. And our scenes, especially when you store geometry, texture, and all that good stuff, are routinely much larger than this. Moreover, scenes, when you think about how they're stored in memory, are quite complicated, right? They include triangles, they include texture maps, they include BRDFs, and all kinds of other things. And so not only are they larger, but they're also unstructured. Now, it turns out that one of the typical tricks that we can do in hardware engineering involves making use of locality in memory, meaning that if I have a bunch of data that's kind of one piece of information after the next lined up in a nice regular pattern in memory. We can kind of retrieve it in bigger chunks in a very efficient fashion. And we'll see that graphic style rendering can really leverage that style structure on the GPU by processing many pixels at once, which are sort of locally located on your memory. Whereas when you're doing ray tracing, you may need to grab from all kinds of different places. You know, like the geometry of one object could be very far in memory from geometry of another. So in effect, the rasterization algorithm can actually stream over the triangles. I can feed, like a card dealer, one triangle at a time to my graphics card. It renders it onto the current scene, and I no longer have to keep the entire set of triangles around. And this allows all kinds of cool parallelization, optimization of your memory, and so on that we couldn't do during ray tracing. So these are the big advantages of rasterization. It's a fixed amount of memory that only scales with the size of the image you want to produce rather than the complexity of the scene. And you can stream over the triangles, essentially allowing for that high complexity of a scene without adding to the space that you need. On the other hand, there are many limitations that are worth mentioning. We're going to see that it's quite difficult to scan convert a lot of primitives. In other words, to figure out that set of pixels to turn on and off. So pretty much modern hardware only supports scan conversion of triangles. Now, we know that basically all surfaces can be approximated with many triangles, but the question is how many, right? So if you have a very complex algebraic surface, you might be able to ray trace it easily, but it could be quite difficult to rasterize. Now, because we're working just with a ton of triangles, we can have all kinds of other artifacts as well. So for instance, if we use a really coarse mesh, like what's on the left-hand side, we might end up with faceting, which is basically just a byproduct of the fact that triangles are flat. Now, what we'll see is that programmable shaders will get rid of a lot of these artifacts by coming up with really clever ways to simulate higher quality rendering, even if our geometry isn't so great. And moreover, modern GPUs can support streaming over a huge number of triangles, so this may be actually kind of an irrelevant concern. However, a more important concern, and one that you guys will all feel the pain of when you do your last assignment in 6837, is that for every rendering effect that you need to write all kinds of different specialized code. There's no unified handling of shadows, reflection, transparency. What are some other cool effects? Like, this, what's this video game Portal, where you look in one area and the rays come out another. Each one of those is going to require a really significant amount of code and usually a significant amount of approximation to implement in practice. One of the really cool things about ray tracing is just the number of different ways that you can extend a ray tracer with like 10 lines of code. And we'll see that that's really not the case for rasterization. It's much more painful to implement many of these techniques. And then finally, rasterization often is subject to overdraw. Now, what does that mean? So as a review from previous slides, when we do ray tracing, we send out a ray, and you only actually do the rendering calculation for the closest object. But in rasterization, we stream over the triangles one after the next and draw them one at a time, which means that we may have to actually rasterize and do lighting computation for many different triangles on top of a single pixel, just by virtue of the way they were ordered, until we find the one that's at the top of the Z buffer. So what that means is that every pixel is touched many times. Now, we'll see many different techniques for reducing overdraw, but the basic issue can remain. On the other hand, we can talk about advantages and disadvantages of ray tracing. The advantages here is that you can basically render anything that you can intersect with a ray. You don't need to just render triangles. You can do curved surfaces, computer-aided design, and so on. And you can also do lots of recursion to allow for shadows and reflections in this nice unified framework. The problem is that ray tracing requires very different complexity for every pixel often. Like some pixels have rays that bounce every which way, some pixels don't. And moreover, you have to keep all of your scene in memory. So that makes it quite hard to implement ray tracing in hardware. We simply don't have that computational coherence. and it's hard to do single instruction multiple data, or SIMD processing. And so traditionally, ray tracing is reserved for high quality, slow rendering, and rasterization is what we use for high speed rendering that needs to be interactive. Now, that's beginning to change. I don't even say beginning to change, it's been changing for a while. It's hardware ray tracing is somehow the holy grail of many hardware manufacturers, and some of the modern demos of real-time ray tracing are extremely impressive. So we'll see how this technology evolves over time, and indeed many modern video games really are ray traced, at least partially, which is pretty cool. Okay, so let's talk about the modern interactive graphics pipeline. I should really add the word interactive here. So in order to draw a scene, we're going to need several different inputs. We'll need the vertices, normals, texture coordinates of the object in our scene, the lighting information and material of those objects, and maybe some information about your camera, like the viewpoint, projection plane, and so on. And then, as with all rendering, the output is just the color and also a depth value, like our Z buffer, for each pixel. And so essentially for our lecture today, we're going to step through all of the different steps of the modern graphics pipeline and give you guys some taste for what's going on. So here's the basic steps. And of course, this is a very modular object, and depending on your particular application, you might need to reorder, reshuffle, or even remove or add steps here. But I think we all kind of agree that these are the basic high-level things that one has to do. So the first thing that we'll do is, as we take in a new triangle, we're going to project its vertices onto the image. What we'll see is that when we rasterize the triangle, in other words, when we generate fragments, we can do that as a purely two-dimensional computation. We don't need to rasterize a 3D object. We just take the 3D vertices, put them on the 2D grid of the image we're going to render, and then figure out what pixels to turn on. Then we need to actually rasterize. So after projecting the vertices, now we need to look at the convex hull of those vertices to figure out which pixels should be lit. So what that means, in effect, is that you can think of a triangle as basically defined by three edge equations, right? That you need to be on one side of each of three edges. So there's sort of three different Boolean values you need to compute. And if you all pass, then you draw a pixel, or at the very least, you generate a fragment. And then finally, you compute the pixel for the fragments that you generated, the color rather, and you test visibility. Now, this is this idea of a Z buffer, that essentially what we're going to do is, as we generate these fragments, we're not just going to generate their color, but we're also going to compute their depth from the camera on the current triangle. This is just like T-min and ray tracing. And we're going to have this really critical little piece of code here, which is going to ask whether the Z value of the current object is closer to the camera than the Z value of what you've currently rendered. And if it is, then you'll update your Z buffer, and in the frame buffer, which stores the actual image that you're generating, you'll store the color. So hopefully you can see that as you iterate over your triangles, you're going to keep replacing the color of whatever's on top until you end up at your final scene. Incidentally, there's one basic idea here that I should mention that I think isn't mentioned in the slides, and that's an idea called double buffering. So we're going to use this term buffer a lot. A buffer is just like a little space in memory that contains, an image or depth values, whatever you're trying to currently compute in your graphics code. One thing that I think is kind of obvious, but maybe we don't think about, rasterization iterates one triangle at a time. I have a piece of memory and I'm going to keep updating it, adding more and more objects to my scene. Obviously, I don't want to connect that piece of memory directly to my computer screen, or else the person using my computer is going to see one object rendered after the next, which can be kind of cool from a sci-fi perspective, but will take you out of your video game, remind you that you're using a computer. So in the double buffering technique, what you do is you have two pieces of memory and a binary digit. And what happens is you render to one piece of memory while you display the other. And as soon as rendering is complete, you flip that digit and then you flip which one is being displayed and which one's being rendered. You go back and forth. So this idea of double buffering is just a nice trick to get around accidentally showing to your computer user what's going on behind the scenes. Okay, so here's the basic steps that we've outlined in the previous slide, now written as pseudocode. So you can see that we take each triangle, we project them onto the computer screen so that they have two-dimensional coordinates. We set up the edge equations, and now we iterate over all the pixels to figure out which ones are inside of the triangle. If they're inside of the triangle, we figure out the depth where it hits, and if it's closer, then we store the value. Now, you can already notice that there are many different variations of the rasterization algorithm. For instance, in this particular piece of pseudocode, we're only calling shade if your z value is closer than what you've already seen. I think this is pretty advisable because otherwise you might spend a lot of time shading pixels that are not visible. But notice that this shade could be called for a value that doesn't actually get used in your final image. So for example, the very first triangle that you draw might be completely occluded by other stuff, but you don't know it yet, and you end up shading all of its vertices. And that's the kind of thing that we're going to try to avoid later on. Okay, so that's the basic idea of rasterization. It's just we're looping over the triangles on the outer loop and the pixels in the inner loop, and we're going to see that that creates for some very different tricks that can make our rasterization technique very efficient. So now we're going to step through each of those steps that I identified in the earlier slide in a little bit more detail. So first, let's talk about this projection step. Now, there's one thing that I think all graphics textbooks kind of implicitly are using that we don't always call out for what it is, and that's the fact that when I view a triangle in 3D, it looks like a triangle in 2D. Now, you know, that somehow sounds, I can't decide if that sounds really simple or really profound, but it's definitely one of those two. But the basic point here is that some geometry structures are preserved and some aren't under camera projection. So for example, if I have train tracks that are parallel in 3D, we know that train tracks are not parallel when I render them on a image. On the other hand, one thing that is true is that if I have a triangle in 3D and I render it on my computer screen, nothing crazy happens. Like the edges of the triangle don't turn into curves or something like that. They could with a weird lens, but for the simple camera projections that we've talked about in this course, triangles get mapped to triangles. So what does that mean? What that means is that we can project the vertices of our triangle onto the screen, and then we can rasterize with no knowledge of the 3D information. Let me repeat that. So you can take the vertices of a 3D triangle, make them points on your 2D image, and those 3 2D points are enough information to figure out which pixels to light up. Now, we've already talked about different camera projections and techniques. There are two that are very typical in rasterization, largely because they take triangles to triangles, like what you're seeing here. And those are the orthographic and the perspective camera transformation. I thought I'd spend 5 minutes reviewing the perspective transformation just to jog your memory a little bit from a lecture long, long ago. So here again is this two-dimensional idea of perspective projection. Basically, your eye looks out into the world, creating this weird object that we call the frustum, which are all the things that are visible inside of this little cone. So the thing about perspective projection is the farther away you go, the more you can see. And in particular, what we do is divide by depth to get the coordinate on the image plane. Now, remember that we basically used a mathematical sleight of hand to make this look like a linear transformation by adding a homogeneous coordinate. So the real coordinate basically takes the position and divides by depth, but that is proportional to xzz. And so one thing that we can do is we can figure out the screen projection using this matrix here. This is again a projection matrix. Now, when we talked about it previously in this course, and I'll admit actually I'm realizing that those earlier materials are the tiniest bit confusing when it comes to the dimensionality of our projection. I might revise them in future offerings of this course. But in any event, this is for two-dimensional projection, but the 3D story is pretty much the same, which is to say that we just take the z coordinate and we want to copy it to the homogeneous coordinate. And so that's the basic projection matrix here. Now, these matrices work perfectly fine in that you really do get the proper 2D projections of 3D points, at least after you divide out by that homogeneous coordinate. But in effect, when we do that division, we're flattening the scene to this z=1 plane. So in other words, we've basically forgotten about the distance of the triangle to the camera. Now, that's perfectly fine for generating fragments, because again, the projection of a 3D triangle onto your scene is still a triangle. But we do need distance information for z buffering, so we actually don't want to forget it. And so there's a really clever trick that lots of people use in computer graphics to actually accomplish this. And the basic trick here is to store 1 over z in your projected image. So in particular, the row that matters to examine our new projection matrix is the one that I've circled here. Remember that previously that row was identical to the 4th row, but now instead we're going to put a 1 all the way on the right. Why do we do that? Well, if I take this vector x, y, z, 1, and I multiply it by this matrix, I'm going to get x, y, 1, z, right? Hopefully we can all agree on that. Remember that matrix multiplication goes left to right, top to bottom. So notice that I've done something kind of funny. This is supposed to be a projection matrix onto my computer screen, but this is still a 3-dimensional coordinate plus a homogeneous coordinate, right? So somehow I still have 4 numbers. Why do I do that? Well, once I dehomogenize, I divide by z, I'm going to get a coordinate x over z, y over z, 1 over z. So in effect, in my camera projection, I'm still keeping around this extra number, which tells me all the depth information that I'm going to need. So when I'm using this for turning on and off fragments, I'm not going to need it. But when I fill in the depth buffer, I'm going to use this information. Okay. So there are many different ways to understand this funny matrix in homogeneous coordinates. Here's a very typical one, is that essentially what you're doing is you're taking your view frustum, this kind of funny shape that grows as you get farther and farther out, and you're transforming it into a cube. One thing you have to be a little bit careful about, though, is that you're flipping the order of the z values when you do that, because you replace z with 1 over z. So anyway, this is just some schematic of what's going on. Essentially, a different way to understand it is that you're kind of converting perspective into an orthogonal projection, but none of this really matters. So the basic point here is that the final image is obtained just by dropping the z coordinate when it comes to figuring out what pixels to turn on, but we're going to need that z coordinate later for depth buffering. Now, there's some details that are worth mentioning. One is that we typically need to worry about precision here. So remember that precision is kind of related to this quantization artifact that we briefly mentioned in the anti-aliasing lecture. The idea that in reality, our computer can't store every possible number, right? When we use floating point, there's little spaces between every number that we do our computation with. And so in particular, one of the big sources of imprecision can come from dividing by a really small number. So let's say that I get my camera really close to an object so that the z value is small. Then when I divide by z, sometimes I can end up with a big loss of precision, which can lead to really bad artifacts. Like essentially what will happen is that the z values will start to be inaccurate, and you might accidentally put one thing on top of another that shouldn't be like that. So a typical thing that we'll do is define 2 values, z near and z far, which are going to be like 2 planes that are close and far to your camera, and we're simply going to ignore fragments that are outside of that range of z values. So in effect, what this does is takes our full view frustum and clips it down a little bit. And it also makes sure that we get the most precision out of our z values possible. Because, for example, we could take that range of z values and map it to the range between 0 and 1. So all of this computation leads us to an object called the canonical view volume, which essentially maps z to some canonical range, often -1 to 1 or 0 to 1. Doesn't really matter. And similarly with your spatial coordinates, like your screen coordinates, x and y. All of this is by convention, and when you go work at a particular video game company, hopefully somebody will tell you out there what coordinate system their rendering code expects, because there's nothing, mathematical or God-given here. These are just standards. So as an example, in OpenGL 1.0, where projection matrices were built in, this matrix would take a form that was a little bit more general than the one that I've shown you in the past. And simply what this is doing is scaling those near and far planes to that canonical range rather than just dividing out by z. And any of these things is fine for rasterization. All that matters is the z ordering is preserved and that the x and y coordinates are correct for fragment generation. Now, one thing you might remember is that OpenGL 1.0 was this sort of fixed function pipeline. Later on in graphics history, we actually removed all that functionality and pushed it to the software developer. That is to say that rather than having to study a textbook saying that OpenGL wants your coordinate system to look like this, we're just going to allow you to put in whatever matrix you want and implement the projection and so on. What that means is that sometimes you have to do a little bit more work and establish a standard with all of your software engineers that you're all going to follow. But it's still worth knowing a few of the terminology from the original OpenGL handbook, because I think a lot of people still use it. That's why we have the, was here. So in particular, a typical thing to do is to actually store two matrices during rasterization. One is called the model view matrix, and the other is called the projection matrix. So here, the model view matrix is doing all of the transformations you need to your 3D geometry to put it in the right place in your 3D scene. And then the projection matrix is the thing that's putting your camera into the right place. And so at the end of the day, when you take your vertices of your geometry and you want to project them onto the screen, you multiply them first by the model view matrix and then by the projection matrix. Finally, you dehomogenize, you divide by W, and what comes out is the position on the screen plus maybe 1 over Z so that you can do your depth buffering. Oof. So anyway, hopefully you guys get the basic point here, which is that when you project a triangle onto the image grid, it still stays a triangle. That's what these homogeneous matrices do. And if you do a small hack to the homogeneous matrix where you swap the Z and the W coordinate rather than basically just throwing away the Z, then you'll still have depth around in addition to your position on the screen. That's the basic message here. Okay, so now that we know where the vertices of the triangle are on our computer screen, the next thing we have to do is actually figure out which pixels to be lit up. So to put it differently, we know the 3 positions of the vertices, and now we got to fill in the insides. Okay, this is rasterization as opposed to projection. So this task is often called scan conversion, and the basic issue here is that your screen is discrete, but of course your primitives can sit anywhere. They're kind of continuous geometric objects, and essentially scan conversion is trying to handle the interaction between discrete and continuous world. So what do we need to do? Well, essentially, we need to compute a discrete approximation in terms of pixels of our objects. Now, conceptually, this is easy, but it turns out that implementing rasterization is actually quite difficult to do in a perfect fashion. I would not want to be the guy that works at NVIDIA and has to implement this stuff. And here's the reason. Rasterization really depends on millions of special cases that you have to develop policies for. We are not going to cover them in this class because they're boring and uninteresting and really difficult. So the really key example that I think is good for appreciating what's going on is, let's say that we render 2 triangles that share an edge. And by bad luck, maybe that edge gets really, really close to the center of some pixel. So remember how the rasterization algorithm works. It'll first maybe render one triangle and generate fragments for every single pixel that intersects that triangle. And then it'll do the same thing for the second triangle. Now, initially, this sounds easy enough, but depending on, for example, really goofy stuff like rounding of floating precision, it could easily be the case that for some fragment that's really close to a shared edge between two triangles, that maybe both triangles generate a fragment on that pixel, or maybe neither one generates a fragment, and suddenly there's a little tiny hole along the seam between these two things. Now, neither of these cases is acceptable. And so what has to happen if you want to implement a perfect rasterization algorithm is you need to worry about that last little bit of precision and accuracy, and make sure that if I have a seamless triangle mesh on my 3D geometry, that it becomes a seamless set of fragments when I generate them on the screen. Now, initially you might say, but Justin, these are like boundary cases. How often do they happen? And unfortunately, the answer is a lot. And the reason is that A, there's a lot of triangles in a modern 3D model. And B, these special cases actually come up because oftentimes when people model, they actually model a 3D scene, they will line the camera up with like the principal axis of your shape, which maybe just happens to be the way the shape was meshed. So these boundary cases really do appear in practice, and the engineers that make scan conversion hardware and algorithms really have to think through every single time any floating point number is rounded to make sure that like they're not little holes sitting in between your triangles, or that they're overlapping fragments with extra computation that you didn't need. It's a really tricky matter, and one of these engineering details that I think at MIT, we're quick to sweep under the rug, but in practice can create huge amounts of headache. In fact, many years ago, when I used to teach intro graphics at Stanford, one year I gave them an assignment, which was just to make an algorithm that, or rather a piece of software that rasterizes two triangles. And I had them run a test that just made sure that every single time you rasterize, you generate exactly one fragment when two triangles share an edge. And the students were pretty much frustrated and hated me. So we don't do that anymore in 837, but it is worth calling out as a challenging thing. So let's talk a little bit more about how to figure out what pixels to light up, kind of maybe ignoring those edge cases for now. So remember that the triangle has 3D edges, but when we project them onto the screen, they become 2D. And now the edges are oriented because the triangle has an inside. So essentially what I can try and do is figure out which pixels are in the inside by figuring out which pixels are on the proper side of all three lines that define my triangle. I think all of you guys could probably do this computation in practice. Essentially, you end up working out the equation of each of these three lines and then checking the sign of the right-hand side there to make sure you're in the inside. I'll let you work out the details at home. Now, this is extremely brute force technique, right? Like essentially you're just looping over every single pixel on your screen to figure out which ones to rasterize. But in any event, this is called the triangle setup step. Oh, I'm sorry. So the triangle setup step is the step where you generate the equations of the lines of the triangle. And then, the actual rasterization step is the one that fills in the insides. Now, I've used this phrase brute force, and I mean it. I mean, in particular, there is a big problem. I'm gonna, circle it with flashing lights here. And what's that problem? Well, remember that our typical 3D scene has a ton of triangles. And now we have a loop over every single pixel on the screen. Well, maybe that's okay if the triangle takes up most of the screen, but then it's not a very interesting 3D scene. The reality is that most of our triangles look more like what I've shown you here. They're really tiny. And so if we really do all of these computations to check if every single pixel is inside of our triangle, for every single triangle, we're wasting a ton of computation. There's a lot of, maybe not overdraw, but a very similar phenomenon. That's why this brute force technique really isn't the one that we use in practice. And so, of course, in practice, people use all kinds of clever ideas to make this rasterization procedure more efficient. So, for example, one easy thing you can do is compute the bounding box of the triangle and only scan over those ones to figure out which ones intersect your triangle. And for example, here you can see that that basically fixed our problem. But that isn't always the best thing to do. So for example, let's say that I have a really slivery diagonal triangle like that. Well, unfortunately, this guy's bounding box is still pretty humongous. At least its axis-aligned bounding box. So in this case, this particular trick isn't enough. So I'm going to let you guys think about that a little bit while we talk about some more details in rasterization, and then we'll return to how we can make it faster. In the meantime, here's some pseudocode for rasterization. Remember that, again, our outer loop is over every triangle. We're going to project the vertices like we talked about in the previous step. Now, what can we do? Well, for each bounding box, we're going to clip the bounding box to the screen limit. What that means is that, like, if I have a triangle that goes outside of the screen, then the bounding box that I really need is maybe here. Doesn't need to be the whole triangle. And now, for each pixel in this bounding box, we evaluate those functions, check their sign, and if they're all positive, we're in the inside. Okay. So obviously this code doesn't deal with visibility, but if you added a z-buffer check, it would. Now, of course, our question should be, well, what can we do to make this function even better, right? And there's many different ways to do it. In fact, I would say about 30, 40, 50 years worth of graphics engineering has gone into essentially making fragment generation more efficient. And there are many different techniques that people use in practice. So here's one idea. So remember that the edge function for every edge is just some linear thing. And one thing to notice is that there's a whole bunch of vertices that all have the same x value or y value, depending on how I stride through this box. And moreover, when I scoot one thing across, essentially what I'm doing is just adding a factor of ai or bi. So what does that mean? Well, it means that we can do our computation, namely evaluating these edge functions, in a more efficient fashion. The way that we do that is, rather than evaluating that whole product at every single pixel, we're instead just going to evaluate it maybe at the first pixel. And now we can move all the way along the line. And each time we do that, we just gain a factor of ai, assuming that y stays constant and the x's are increasing by 1. And already, this saves us 2 multiplications and 2 additions per pixel. Now, I'm introducing this goofy technique, but the reality is that even though we're used to thinking in algorithms about like big O stuff, anything we can do in rendering to increase the efficiency of our technique, even if it's just shaving off a few adds or multiplies, is going to make our rendering a heck of a lot faster. The reason is that we're doing this tons and tons and tons of time. Remember that there are tons of pixels on your screen, and that's being multiplied potentially by the number of triangles that we're trying to render. Now, if we want to be really sneaky and we want to avoid having to recompute that EI in every single row, we can also zigzag up and down and essentially just change whether we're incrementing the multiple of A or B, or subtracting or adding, kind of shown in this pattern here. So hopefully this gives you some idea for the flavors of techniques that people use to shave off computation during rasterization procedure. In fact, there are all kinds of really clever rasterization tricks out there. So one more sophisticated technique that was proposed by Mick Cool, also a great name, is to use a Hilbert curve, one of these space filling curves, to traverse the pixels on a screen. This is kind of useful, I think, because they're a little more local or compact relative to doing things line by line. Boy, I wish my neighbors weren't scooting around their furniture pretty much constantly. Okay, so anyway, notice that this technique does not reduce the amount of computation we have to do per row. It just reduces, or rather, oh boy, it does reduce the amount of computation that we do per row simply by reducing the number of adds and multiplies per pixel. But we still have this problem that if we have a long, slivery diagonal triangle, its bounding box takes up a lot of space. So let's return to this question of whether we can do any better. So for example, here is a pretty long triangle, and you can see that there's a bunch of space here where you essentially are doing wasted computation. All right. So of course, if I'm asking this question, the answer is yes, we can do faster. We can be more efficient. And let's see one strategy for doing that. In particular, notice that there are big regions, we could even call them superpixels, where we really don't need to do any computation. So for example, let's say that I checked all 4 corners of this box, and I determined that none of them intersected the triangle. Well, then we might be tempted to say, oh, well, then I don't have to rasterize that box. But of course, that's not true. Here's a counterexample. However, if they're all on the same side of all 3 lines, right, like they're all in this little region, then we can. So we might want to leverage this basic observation that we want to eliminate big blocks of pixels at a time, prune them out. So one algorithm that uses that basic observation, which I think is one of the ones that's more commonly implemented in your graphics card, is called hierarchical rasterization. The basic idea here is that we're going to take our screen, and we're going to divide it into blocks of pixels. For example, here we can see 4 by 4 blocks. And we're going to come up with conservative tests that tell us whether or not the entire block of pixels intersects the triangle. And if it doesn't, so for example, the blue blocks shown here, right, there's 1, 2, 3, 4 of them, then essentially we don't need to do the checks in the interior, and that can skip a large piece of the screen at once. Now, typically when people implement this, at least, circa 2005, but I actually don't think that this is likely to change over time all that much. There's just 2 levels of hierarchy, so maybe you do it in, 16 by 16 chunks of pixels and then fill in the inside. But already, that's a 16 squared factor of improvement over your basic rasterization technique. Now, it's not hard to come up with a conservative test of whether or not your axis aligned block has any intersection with your triangle at all, but it is something you have to do carefully. So just similarly to like when we talked about KD trees and ray tracing, there's some amount of care that has to go into this style of computation. Okay. One thing that is worth noting is that you can also check if an entire block is inside of a triangle and then light up all of its pixels. That can save a little bit of computation as well, but not that much because you still have to fill in the Z buffer because it could be that, the 2D triangle is visible on the screen, but it's occluded. Now, I'm going to pause here and note that the rasterization techniques that I've been telling you about are like super uninteresting, algorithmically speaking. I mean, if you think about it, all of these are the world's dumbest techniques, right? We're just like taking every single pixel in a square and checking manually if that pixel intersects your triangle or not. And a reasonable question you might ask is like, well, what the heck? Like, we had all these cool algorithms, KD trees and OCT trees and bounding volume hierarchies and so on to eliminate computation and ray tracing. Like, surely there's got to be clever tricks here. And indeed there are, but there's something else at play, which is that your graphics card is this really interesting beast. It's really good at a very particular type of calculation, which is called single instruction multiple data, or SIMD. The basic idea is that your graphics card is really good at running little short segments of code over and over and over again with different inputs, and then storing the result on like a little grid of memory. That's what that architecture is built for. We're going to talk more about that in future lectures. What that means is that these sorts of algorithms that are just dividing things into blocks and then iterating over them go ridiculously quickly in your graphics card and can be parallelized in all kinds of different ways. I mean, these are what we might call embarrassingly parallel algorithms, in that every single pixel's inside-outside test is tested independently from every other pixel's inside-outside test. There are clever algorithms for rasterization that, for example, scale in the number of pixels that you're going to light up, whereas these ones scale in like the size of the bounding box. But they're often quite difficult to parallelize, and sadly, if I were teaching this class 15 years ago, we'd spend a lot of time deriving these algorithms. But nowadays, it's actually not really necessary. Your graphics card probably does a more brain-dead thing. Or it does something really sophisticated, but is outside of this scope in a different way because it has to do with parallel computing. But just for fun, I can mention some old school rasterization tricks. So one old school rasterization trick that's kind of fun would be that you essentially first render the boundary curve of your triangle as 3 lines. And you would do so with an algorithm that is guaranteed to kind of produce a contiguous line of pixels, so they all kind of share a boundary edge. And then, as you do that, you just fill in horizontally from the left line to the right line. This is more annoying to implement, and it's typically not a whole lot faster, but there's some fun algorithms for drawing lines. So if you're an algorithm student and you want to learn more, there's some really clever tricks for drawing straight lines and curves that are fun to read about. I used to teach this stuff. It makes me sad that I've had to remove it. But I would encourage you to Google Bresenham's algorithm for the basic rasterization trick and what you probably would have implemented in rasterization before graphics cards became these parallel computing beasts that they are today. Now, there are all kinds of other techniques out there for rasterization and considerations that you have to make when you're drawing your scene. So one of them that we've talked about a little bit is depth. So for example, we should be a bit careful when we handle depth. You know, obviously if the point Z is bigger than your IZ, then assuming that your eye is pointing in the plus Z direction here, you should render a point. But when you homogenize, you might accidentally divide by a negative number. And in that case, it might make you feel like you should project that object, I guess, flipped over onto your eye. So during your Z buffer test, you need to be a little bit careful about that and check the sign of Z. And in fact, moreover, you can even divide by 0, right, when PZ is equal to your IZ, which can actually happen quite a bit. So the reason that this happens is if I'm rasterizing an object which maybe starts visible and then ends up behind the camera, then there'll be some point of intersection where that can happen. Oops, I guess it's here. And so in that kind of case, you can divide by 0, which is really troubling. So a very typical thing that people do is just before rendering the scene, taking the geometry and just clipping it to the view frustum. So clipping means that before I stream the triangle to the GPU at all, I just check its vertices. So if the triangle is completely behind my eye, I just throw it away. I don't even stream it to the graphics card for rasterization. And maybe if it intersects the view frustum, I actually do a tiny bit of geometric computation to figure out the geometry of that intersection rather than rasterizing the whole thing. So this is the idea of clipping. So here we might, I guess it's a little dark. We might behead the cow here and essentially eliminate portions of objects that are outside the view frustum. There's a lot of different reasons to do that. I mean, partially it simplifies your Z-buffer test. More importantly, there's a lot of triangles here. And if we don't have to rasterize them at all, then that's, less computational work that we have to do. So a very typical thing to do is not only to clip objects based on what's visible, but often to include the near and far plane, as we've already discussed, and clip geometry that's outside of that range. So there's a lot of reasons to do that. So for one, you can avoid degeneracies like drawing points that are behind your eye or dividing by 0 and getting overflow. This can also make your rendering more efficient. So one idea would be to put a bounding box around your entire object. And if that entire object doesn't intersect your view frustum, then you don't even have to look at any of the triangles there. And so this idea is called view frustum culling, that at the object level, we can check the bounding box of your object. And if the whole darn thing is outside your view frustum, you don't need to send any of the triangles to the graphics card, and you can skip right over it, which can make things much more efficient. Incidentally, there are all kinds of clever tricks that people used to use to reduce the number of triangles that you had to stream to your graphics card. And the kind of fun thing is that, we often talk about, art affecting science and science affecting art. In this case, the technology definitely affected the art that we saw. So one thing you might have noticed about video games that old guys like me like to play is that they often took place in, dungeons and basements and houses with small rooms. Now, maybe that said something about people's attitudes in the 1980s, but in addition to that, it made rendering a heck of a lot easier. So a very typical thing people would do is design levels in video games with very small doors between the levels. And one reason for doing that is that if there's a character here, then their view frustum cannot, I guess in this case kind of looks like this, see anything in one of the rooms that's two things far apart. And so actually by designing your levels in a clever way, you end up reducing the amount of computation that you have to do, because if there's a complex object 2 rooms away, we know that it's not visible. And in fact, we don't even have to load that scene into memory. And so this was like a clever way that people could design their video game levels to reduce the complexity of the rendering procedure. And it's related to view frustum culling and all these different tricks, which are essentially just trying to throw away objects that are not visible, rather than spend a bunch of time generating fragments that you can't see anyway. Now, there are other rasterization algorithms out there, and they're worth mentioning. So one nice idea, which I do think gets implemented sometimes, is called homogeneous rasterization. And the idea here is, rather than rasterizing on your screen, right, like making sure that all of your triangles are visible, forgetting the z-coordinate altogether, and then turning on pixels, a different technique is to keep that 3D information around and generate it during the rasterization procedure. And this leads to basically very similar mathematics, but does eliminate some of this clipping procedure. What's the basic motivation? Well, the slide isn't wrong. Clipping is annoying. So in particular, like let's say here's one side of my view frustum, and I have a triangle that starts visible, but then ends up going inside or outside of the view frustum partially. Notice that the visible part of this triangle isn't a triangle anymore. Like here it's a quad. So I would actually have to send 2 triangles to my GPU. And as you can imagine, there are all kinds of special cases that you have to implement here. So because clipping is annoying, in homogeneous rasterization, we avoid it by doing a different trick, which is to do 3D computation instead. So here's the basic idea. Let's say I take the vertices of a triangle, and now rather than projecting them onto the screen, that's the 2D version, I'm instead going to do everything in 3D. Here's how I'm going to do that. I'll take each edge of my triangle. For example, here's one. And I'm going to form a new triangle, which is that edge plus my eye. So, oops, that was supposed to be a straight line. So why do that? Well, remember that 3 points define a plane. So in particular, now I have 3 planes corresponding to the 3 edges of my triangle. So again, each plane contains my eye and 2 vertices of the triangle, as shown on the right-hand side. Why do that? Well, what are all of the different points that are visible in my eye? Well, they're all the different points that lie on the proper side of these 3 planes. And so this is just a different computation that you can do that essentially replaces the 2D edge equation with a 3D one. So essentially it's still a half space, it's just a 3-dimensional computation. So then what do we do in homogeneous rasterization? Well, we actually think of pixels as generating fragments in 3D that just happen to have z-coordinate equal to 1. And now we just check if this 3D point is inside of the cone formed by those three planes. And so this turns out to avoid many of the different clipping things that are necessary in the previous 2D algorithm that we talked about. We simply don't have to shield against these special cases, like something going behind your eye. And so somehow the code that you get is much more simple, right? It's just draw the pixel if these three plane equations all pass, rather than having to check, like, draw the pixel if the three half space equations pass and the pixel isn't behind your eye and you didn't clip and all that stuff. Okay. So this works for triangles behind your eye. It's still using linear tests, and you can still use all these incremental tricks we talked about before, which is kind of nice. You don't have to clip anymore. On the other hand, clipping can be useful because it can reduce the amount of computation that your rasterizer has to do. So it's just worth being aware. This is another technique out there. So again, homogeneous rasterization uses the equations of planes rather than the equations of lines to determine what's visible. The reason is that you don't have to clip out stuff outside the view frustum before you do your rasterization. Okay, so now that we've figured out which pixels are inside of the triangle and projected the triangle onto the screen, of course, there's still many steps left in the rendering procedure. We're going to largely defer on computing per pixel color. So we've already discussed the important content, like what is a BRDF, but we'll need to give a little bit more information on how we can evaluate BRDFs on your graphics card rather than as part of a ray tracer. So for now, we're just going to defer on this. What we're going to see is that there's a really useful piece of code called a pixel shader, which is what we're going to implement in order to evaluate BRDFs. Essentially, a pixel shader gets called every time a fragment is generated. Let me repeat that. A pixel shader is called whenever a fragment is generated. Remember that multiple fragments can intersect a pixel, or no fragments can intersect a pixel, like we talked about at the beginning of this lecture. But in any event, once you call your pixel shader, that's where you can do your shading computation. In fact, that's where the term shader comes from. Okay, and then finally, we can test our visibility, update our frame buffer, and so on. And so I thought for just a few seconds, we'll add a bit more detail on the Z buffer, because it really is a critical idea in the computer graphics universe. I don't think it's too difficult to justify why visibility is really critical in graphics. But the basic challenge here is to make sure that we can determine which parts are visible and in front at a per pixel basis, right? So for example, this object starts out visible and then ends up invisible behind the scene. This is a very typical test case, which I can never draw properly, where you take 3 sticks and you stack them up. Let's see if I can manage. So here's one stick. Here is a second one. Oops. Maybe I have a curved stick for the third guy. So here's his cap. So one question you might ask is which stick is on top? And of course, the answer is none. There are different locations where each of these 3 objects is on the bottom of my scene. Essentially, this is just a simple motivator for why something called the painter's algorithm fails. So if you look at really old graphics hardware, like before people, had critical thinking, oftentimes they used a technique called the painter's algorithm. So this was, I don't even know why we give it a name. Essentially, the painter's algorithm just draws one object at a time. And just obliterates whatever is underneath it. And sometimes that can work. I mean, there are many scenes where the objects are really layered one after the next. But of course, there are many, like this scene here, where the painter's algorithm would fail. And so essentially, that's why visibility matters. There's not like a clever ordering to all of your objects where you can do you can eliminate visibility detection altogether. So of course, in ray casting, we did visibility detection by computing the closest t. But now that we've swapped our loops between pixel and object, we can't really do that anymore. We need a new alternative. So as I've already alluded to in this lecture, essentially what we're going to do is, in addition to storing color at every pixel, we're going to store depth. And that object is called the Z buffer. So the basic point is that when I generate a fragment, I'm going to also generate a value, which is how far that fragment is from the camera. And if that pixel is already farther than the Z value of the current object that I have sitting on the buffer, then I'm just going to throw that pixel away. So for example, we see an image of a Z buffer here. You can kind of see the house sitting at some constant depth from the camera, whereas the ground is going farther and farther away from the screen. Okay. Uh-oh, my screen disconnected. Hopefully that's still working. Okay, so here's some pseudocode for what a Z buffer looks like. So basically all we're doing here is we keep taking our rasterization code and making it a little bit more complicated. So here, notice that there's still a loop over every triangle. We project every triangle onto the screen. We figure out all the pixels that are visible on the screen except for depth. So this is just saying, if there were no other objects in the universe, would I be able to see that pixel in that triangle? Then you compute the Z value in the triangle, and only if you're inside and the Z buffer is not closer do you keep the color and put it on the screen. And we'll see that this technique works even for difficult cases like those 3 stacked up sticks that we talked about before. Okay, so despite some chaos going on in the apartment above mine, we managed to make it through. So that's our basic introduction to the rasterization algorithm. Again, rasterization from 1,000 miles away is just switching the order of the for loops in rendering. So whereas in ray tracing, our outermost for loop was over pixels, and then each pixel iterated over all the objects to find the closest one to the camera. In rasterization, we draw our scene one object at a time over all the different pixels. So what that means is that each pixel might get touched more than once. Doing that requires a lot of adaptation, right? Figuring out which object is closest to the screen, we accomplish using the Z buffer. And to make rasterization more efficient, we use techniques like bounding box intersection or even hierarchical bounding boxes, essentially to eliminate pixels where we know that we can't see the object and we don't need to generate a fragment. Now, this is just the beginning of our discussion of rasterization, and rasterization will occupy most of the rest of our discussion in 6837. So in our next lecture, we'll talk more about how to actually compute the Z values in the Z buffer, and we'll adapt methods like texture mapping, which we already had in ray tracing, to this new parallel computing universe that we have in the rasterization setup. So with that, I'll see you next time.